Okay, here we are back to part two. I have quite a short window of opportunity, about 15 minutes, but I thought I'd get on and make part two. We'll go get through as much as we can in 15 minutes, and then I will come back for part three. So, theory of torque production. So we know how a rotating magnetic field is established around the stator of a three-phase induction motor, right? We have a 120 degrees separation of phases, which creates a rotation. But how does this produce torque in the rotor to enable it to drive a load? So the rotor is what's turning, that's driving the load. So how does our rotating magnetic field work? What does it do? So consider a rotating magnetic field sweeping past a stationary rotor. So our rotor is stationary and rotating magnetic field around it. The flux from the stator field cuts the rotor conductors and induces an EMF within these conductors. So we've conductors, either windings or the bar conductors in our squirrel cage rotor. We have conductors inside the rotor. Because the rotor winding is made up of several closed circuits, that is the windings in this, or the rotor bars which are joined at the ends, remember, with the end caps. So we have those closed circuits, so currents will flow within them. The rotor currents will then set up a magnetic field that interacts with the rotating stator magnetic field to produce torque. The magnitude of this torque depends on the relative motion between the rotating field and the rotor. The greater the difference in relative motion, the greater the torque and the rotor acceleration. The torque causes the rotor to run in the same direction as the rotating field and tries to catch up with it. As the rotor speed approaches that of the rotating field, the torque reduces. The rotor speed settles when the motor produces enough torque to drive the load. Note, the rotor EMF and current are produced purely by electromagnetic induction. There is no electrical connection between stator and rotor. It is for that reason that the name induction motor has evolved for this type of motor. Now, figure A and B show the interaction of the magnetic fields as the stator flux, that's the north pole, passes over the rotor bar. This produces a magnetic field around the rotor conductor, which reacts with the stator field to produce torque. The direction of this torque is perpetuated as shown in figure B, which shows the resultant rotor field as the opposite. Which shows the resultant rotor field as the opposite pole sweeps over the rotor, inducing current in the reverse direction. Use Fleming's left-hand rule to check the direction of rotation taken by the rotor. To check that the direction of rotation taken by the rotor for both cases. Okay, what are we talking about here? So I mentioned in the previous video that if we had that rotating magnetic field happening inside the stator and we just put a magnet in there, the magnet's going to follow that rotating magnetic field. And that's what we have here. So we have the magnetic field in the stator is inducing a magnetic field, or inducing a current into the rotor bars, into the conductors in the rotor, and then that current that's flowing will then produce a magnetic field in the rotor. So now we have, just take that for what it is. We have two magnetic fields, one in the stator, one in the rotor. So essentially now we've got, two magnets. Now if I put two magnets together, they're just going to attract each other, right? They'll just attract, or depending on the poles, they might repel. But that force will happen once. It'll happen in the same direction, and then once my two magnets are either attracted together and joined, or pushed apart so that the magnetic fields are too far away apart to interact, then they're going to stop interacting. The motion will cease. They will just be in a stasis, which is nice. And that would happen theoretically inside our motor as well. But we continuously change that magnetic field because of our rotating magnetic field, because of our the sine waves happening in our windings. The magnetic field is changing all the time. It's rotating. So then my rotor is going to continuously move. And if we think about it, the easiest way to understand this is the stator is a magnet, the rotor is the magnet. The rotor is trying to is attracted to the rotor magnet is attracted to the stator magnet. It's trying to, just like if I had two magnets, it's trying to touch. If I had two magnets, one here, and I just keep pulling this one away slowly, and this one was attracted to it, in theory, right, if I got the right speed, I'd have to be, have the right distance and the right speed and stuff, but if you think about it, in theory, I could move that magnet. And the same thing happens here. As that rotating magnetic field goes around, the rotor follows it. attracted to it. Now, when it says that the distance between the two magnetic fields gives us torque, well, what's happening there? Well, what we're saying there is if the north pole of the rotating magnetic field is progressed to here, but the north pole of the rotor is here, then this is my distance between the two. The rotor is going to try and catch up, but of course the stator magnetic field is moving, so the rotor has to follow it. Now, the greater the distance, the bigger the pull for my rotor to catch the stator, and I get a greater amount of pull. There's a greater force pulling it. Once they're right next to each other, then there's not much force pulling it at all, is there? Because they're right next to each other. That's like that stasis that I talked about. Once the magnets are in line with each other, in theory, the rotor will run at the same speed as the magnetic field, right? The magnetic field is turning around at a certain speed. The rotor just follows it, and they go at the same speed. In reality, that's not true. As I start to put a load on the rotor, it will slow down. As it slows down, of course, then the distance between the rotating magnetic field and the actual rotation of the rotor will then increase, which then increases my torque. And it will continue to slow down, and torque will continue to increase until we reach a steady state in which the torque produced is the same. The torque produced is the same as the speed that we have. So, I'm sorry, the torque produced is the same as the load that we have on the rotor, and then it will stay there. If I take load off the rotor, then less torque is required. So the rotor will speed up. If I put load on the motor, it will slow down until it gets to the point where it's producing enough torque. Remember, more torque is produced at slower speeds until enough torque is produced that it will stick at that speed. And that's essentially what this is saying here. Three-phase motor calculations, motor speed. Again, I said this in our single-phase stuff. I haven't mentioned it in the three-phase stuff, but again, there's some really great videos on our Canvas page that talk a lot more and will show you examples. You'll be able to see the wound rotor, squirrel cage motor, see the motor turning. Just going to give you a much better understanding of what is happening with all of these concepts we're talking about in real life that I can't give you here. So go and find those. Go and find those videos. Definitely watch those videos. It'll make what I'm saying make a hell of a lot more sense. Okay, so as you continue to study the induction motor, you will come across frequently used terms and formula with which you need to become familiar. These include synchronous speed, slip speed, and slip, and the formulas for calculating them. Now, all of this stuff is actually, I think this is reasonably straightforward. So a little bit of maths, but it's not too dangerous. Don't worry about it. So synchronous speed, this is the speed of the magnetic field produced by the stator windings as it rotates around the stator housing. So that's how fast the rotating magnetic field is going. This speed is measured in revolutions per minute, so RPM. It is determined by the frequency of the supply and the number of poles in the motor. We've talked about this before, right? How fast it's rotating depends on the frequency of supply, obviously, because that tells us how quickly each of those poles becomes a north and a south. And the faster it becomes north and south, and the faster the magnetic field is rotating. And then the number of poles in the motor. So I can't increase the number of phases, but I can increase the number of poles. So that's how many times each phase appears on my stator. And the more poles I have, if I double the poles, I'm doubling my speed. It's important to recognize the difference between synchronous speed and rotor speed, which in the standard induction motor will be slower than synchronous speed. So that is exactly what I said 2 minutes ago, that the rotor speed will never be quite the same speed as the speed of the rotating magnetic field. That rotating magnetic field will always be faster. So the rotating magnetic field, also known as synchronous speed, is the theoretical speed of the motor, but it's not the real speed of the motor. If you saw a motor that said 1500 revs per minute, that would be synchronous speed. The actual speed is going to be somewhat less than that. So the synchronous speed of an induction motor can be calculated using the formula in sync. So synchronous speed equals 60. So we're using 60 to convert seconds into minutes. So 60 times frequency, because frequency is the number of positive peaks, so number of cycles per second. So I multiply it by 60 to get number of cycles per minute, and I divide that by the number of poles. or a number of pairs of poles. And this number of pairs of poles per phase. So if I have 2 poles, so I just have one north and one south for each phase. So it's a 2-pole motor. Then it will be a 2-pole motor. So I use one. It'll be here. Will be one pair of poles, a north and a south. If I had 2 poles, 4 poles per phase. So theoretically, then I have 3 phases, 4 poles. I've got 12 poles on my motor. But this wants to know per phase. So it's going to be 2 pairs of poles per phase. So it'll be 60 times frequency. Now frequency in real life is always going to be 50, right? We might use a different frequency for theoretical calculations, but in real life it'll always be 50 because it's the only supply that we have. Unless you go to America, in which case it'll be 60. But so that'll be always be 50. So the top line there will be 3,000, 60 times 50, 60 revolutions. Frequency is 50 revolutions per second, or 50 cycles per second, times 60 makes 3,000 cycles per minute. We divide that by the number of poles, or number of pairs of poles. So if it was a 2-pole motor, it would be 3,000 divided by 1. 3,000. If it was a 4-pole motor, then I've got 2 pairs of poles, so it's going to be 3,000 divided by 2, which would be 1,500. And that's why I say, if your nameplate on your motor says 1,500 revolutions per minute at 50 hertz, I know that that's a theoretical speed, because that's 60 times 50 divided by 2 pairs of poles, 1,500 revolutions per minute, which is a standard speed. Obviously, you can work out from this by now that the number of pairs of poles is limited. It can be 1, 2, 3. It's always going to be a number of poles will always be even because it has to be in pairs. So we can have 1 pair of poles, which would be 2 poles, 2 pairs of poles, 4 poles, 3 pairs of poles will be 6 poles. So that number at the bottom, pairs of poles, will be 1, 2, 3. So we have a limited number. We have a limited number of motor speeds that we can have, because this number here will either be 1, 2, 3. The number at the top will always be 3,000. So we're going to have 3,000, 1,500, 1,000, 750. Those will be our standard speeds. Slip speed. So if the rotor succeeded in catching up with the rotating magnetic field, as I said, the magnetic field is rotating at a specific speed and that rotor is trying to catch it, there'd be no relative motion, so no current flow in the rotor, therefore no torque to maintain rotation. The rotor therefore always runs at a speed less than synchronous speed. It's always trying to catch up. As soon as it catches up, the torque disappears and it's going to slow down, or there'll be no torque, so it will slow down. So it's always going to be a little bit, and the greater the load we put on it, the bigger that difference will be. The rotor always runs at a speed less than synchronous speed. The difference between synchronous speed, that's the speed of the rotating magnetic field, or the theoretical speed of our motor. And so the difference between synchronous speed and the actual speed of the rotor is called the slip. So it's just going to be synchronous speed minus actual speed. Slip is usually expressed as a percentage of synchronous speed. At standstill, when the rotor is not turning, the slip is 100% because the magnetic field is turning, but the rotor is stalled. So it would be 100% slip. If an induction motor could run at synchronous speed, then the slip would be 0 because my speed of my magnetic field would be the same as my speed of rotor. Now in practice, the slip at full load speed varies from 2% in large motors to about 10% in very small motors. So we're going to do synchronous speed, that's our theoretical full speed, minus the actual full speed is our slip speed, and then our slip percentage is going to be our synchronous speed minus our actual speed divided by synchronous speed times 100. So we're just working out the percentage of synchronous speed that our slip speed represents. Okay, I'm going to hold there. The second number for our quiz is 1. Second digit in our quiz is 1. And I'm going to stop there and I'll come back for part 3 in a moment.